Hello, everyone. This is Peter, and this is The Burning Question. I'm here today with Peter Burgess, who's the managing director of Rainbow Bee Eater. They're in Australia, located in Australia, Melbourne. Is that right? I'm probably not
That's
saying it right.
correct. Yep,
Okay.
Melbourne. Yep.
And welcome to the show. Thanks so much for taking a little time. Why don't you describe a little bit about how you got into biochar and the founding of Rainbow Bee Eater?
Well, as people can see, I'm not a kid, so I've actually done a few things before I founded this company called Rainbow Beta. I'm a mining engineer, and I spent a long time working with an American company called Alcoa, the aluminum company of America, and senior leadership roles, running various things, mines, refineries, smelters, and selling product all over the world. So I've seen a lot of manufacturing processes. I've seen a lot of the environmental consequences of our carbon intensive way of mining and producing product, and then recycling or not recycling product. And I left corporate life about 15 years ago and got very interested in the whole concern that we all have, or many of us have, about global warming, and looked around at what we in Australia could do about that. I was living in the States when I was with Alcoa. I moved back to Australia, and I realised that the debate about global warming had really been overtaken in Australia by the energy companies, basically, or companies that had a vested interest in nothing much changing. And so I started looking around for how can a large country like Australia do something to offset this carbon risk. Australia is a very large exporter of greenhouse gases in the form of coal and natural gas, and we have many carbon intensive industries, including aluminium and steel. So I was looking for what's a way of pulling some of that carbon back out of the sky, and got interested in the usual things, wind and solar and geothermal, none of which were carbon negative, and then came across this ancient idea of converting biomass residues into charcoal. And my own industry, I trained as a metallurgist, and the early metallurgy for thousands of years was done with charcoal that was made from forests. A lot of the forests that were cleared in Europe and the United Kingdom were cleared to make charcoal to smelt copper or steel or something like that. So it's an ancient technology, and it was a dirty technology too, because while a lot of the carbon that's in the tree or whatever the biomass goes into the biochar, a lot of the carbon also was let off as smoke, and toxic smoke. So those old technologies were not a way to create charcoal. However, it was starting to be understood that if we did that process of converting biomass residues into charcoal in a clean way, then we could not only make charcoal and put it back in the ground, where it has many benefits, which we'll come to, I'm sure, but we could also capture the bioenergy in a clean way on the way past. So that's how this all started. I met my business partner, who's a third generation wheat farmer, Ian Stanley, at the world's first biochar conference, and we decided to work together to create something. So that's the start of the story, I guess, Peter.
That's super. Oh, it's super interesting to hear your background, kind of thinking about it from, okay, I understand how large factories operate. Okay, now apply biochar to that. It's super interesting. So, I've seen a little bit of video, and the video, I'll link to the video in the notes here. But you guys are working with a greenhouse and I guess farming or gardening company called HoloFresh. Is that right? And I think this is a super interesting thing that everyone in the biochar community talks about, which is how do you make biochar while also using the process heat? And so why don't you describe how you developed this relationship with HoloFresh, and then the technology that you developed to execute on the vision that you guys had.
Yep. So maybe I'll do those two in reverse order. So let me just talk about how we came to develop the technology, because we never set out to develop a technology. When Ian Stanley and I got together, it was clear that Australia excuse me, a lot of biomass residues that were burnt or landfilled, millions of tonnes a year, that people who live in cities just don't understand how much plantation, forestry residue, how much grain crop residue is just burnt, just piled up and burnt each year, because that's the only thing to do with it. And if it's not burnt, then it becomes another problem for various reasons. And so we realised there was plenty of biomass. And so we actually went around the world and looked at all the technologies that existed already for converting biomass residues like that into both energy and charcoal. And what we found was that all of them, really the good ones that we'd be proud to operate in your community or my community, that were safe and so on, all required government subsidy to be financially capable. Why was that? They all struggled with how to make a clean gas. So I talked about the old processes made smoke. So how do you turn that into a clean gas that you can use in a turbine or an internal combustion engine or a boiler to make heat or electricity? And there were many good technologies doing that, but the way they cleaned up the gas was expensive. And so therefore they all relied on government subsidy to make a living. And so therefore they weren't making a very good living. So anyway, to cut a long story short, we decided we would develop our own technology that wouldn't rely on government subsidy. And we realised to do that, the process had to make clean syngas in one process step. It wouldn't be good enough to make good biochar and dirty syngas and then spend a lot of money cleaning up the syngas. It had to do all that in one process. So what we came up with, and you can see information about this on the website, and there's now a patent for it. It's a long tube that's about 8 metres in length and about 600 millimetres in diameter. And the biomass is pushed in one end, it's stuffed in one end at ambient temperature. And it's pushed towards what I'll call the hot end, the reactor. And at the reactor, we introduce a little bit of air, and we're burning a little bit of, it's not the wood by that stage, we're burning a little bit of the charcoal and the gas and the oils and the tars that are at that end of the process. The charcoal keeps going in the same direction, so the biomass is going that way and the charcoal keeps going. The syngas, the only way it can get out is to go backwards through the biomass. And the biomass is like a cigarette filter. It's continually coming in. I don't remember which way I did my fingers now, but biomass coming in. Right. So the cigarette filter is moving towards this hot end of the reactor here, and the gas is going backwards through that incoming biomass. And so the oils and tars and the smoke, all the stuff that made that smoke toxic from those old processes and a lot of the new processes gets trapped by the incoming biomass and returned to the reactor and destroyed and turned into either gas or biochar. So that took us years, and by about 2017 we were happy with that. We were making clean gas and good biochar, and we started looking around for a courageous first customer. And of course, first customers have to be courageous because there were still many things that we had to prove. So we found Ian Lyons and his family, who run the glass house that you mentioned outside Mount Gambier in South Australia. There they grow basil and oregano and various herbs for the Australian supermarket chains, and they grow this hydroponically. It's quite a cold area of Australia, and so the glasshouse needs heat for probably 9 or 10 months of the year. They were using waste oil to provide that heat. They were burning waste oil in a boiler and circulating hot water through the glasshouse. So the idea was we would come along with our technology and utilise waste wood and create a clean syngas that could be burned in a boiler to make hot water, and the biochar could be used in a local composting operation. And so that's essentially what we've set up, and that's now been operating for more than 12 months. So waste wood. So this is cleaned up construction and demolition timber that would otherwise be burnt or landfilled. It's sized down to about that size, about less than an inch, and brought to the Holofresh site in trailers, in moving floor trailers. And the moving floor trailer connects up to our computer, our process control computer, and feeds the material in on a continuous basis 24 hours a day. The biochar at the other end of the process is taken away in a bin by that same company that supplied the material and put into their composting process. They're a large organics recycler, so they love the biochar. They can add it to the composting process. The syngas we burn in a modern, efficient boiler, and that makes hot water for the glasshouse. And already that's reduced substantially the energy costs of HoloFresh, and it's made it a very carbon negative operation. The next stages, which will happen over the next few months, the gas is clean enough to put into an engine. So we've got an engine sitting there with a generator attached to it. So we will start to generate electricity in the next few months.
Wow.
And then the third leg of that stool is we believe the flue gas from the boiler, probably with a little bit more filtration, will be a good source of CO2 for the glasshouse.
Wow. Okay.
So from this waste wood, there will come heat, electricity, and CO2 for the glasshouse. Many plants like CO2. All plants love CO2.
Right, but high levels of concentrations of CO2.
Yes.
So, that sounds like an incredible kind of system. What kind of scale are we talking about?
So this single module makes about 1 megawatt of syngas. It uses about 3/4 of a tonne an hour of moist wood that's coming in, and makes about 400 kilograms an hour of moist biochar. Kilograms, 2.2 pounds. Yeah.
Right. So, what's your yield of biochar? I mean, how much carbon do you think is being captured from the incoming biomass?
Yeah. So it's very carbon negative. We've just done a life cycle analysis because we're going down the path of getting some carbon drawdown certificates from a Finnish broker called Puro, and so we've done a life cycle analysis recently that we've just had checked by a third party life cycle analyst. So the numbers are something like this: for every dry tonne of biochar that goes out, we trap about 3 tonnes of CO2.
That's great.
The overall life cycle, if you look at the avoided emissions because we're not landfilling or burning the biomass, and the effect of the biochar in the soil, you get a very large number. Like it'll be something like 8 tonnes of CO2 per tonne of biochar, something like that.
Right. Yeah, it's interesting, right? And I think the biochar community has this. That has to deal with this in a repeat basis, which is what do we account for and what do we do about this, right? Is it just the carbon in the wood? Okay, what about what happens if you plant it in the ground? It increases the viability of the soil, or growing capacity of the soil. Do you want that? I think we're all at the place where if we can get compensated for the the carbon in the biochar, that would be a huge step. So why don't you just a little bit, where are you in the process?
Sorry, go ahead.
No, go ahead. Where are you in the process of are you able to sell credits for your biochar now, or are you in the process of doing that?
Yeah, first let me say we always assumed that this wouldn't happen. So our basis for developing the technology was that the business system needs to be viable without any government subsidies or carbon credits, whether they be voluntary or legislated, whatever that is. So this has come along as a nice surprise for us. It will certainly help us build more projects more rapidly because it just makes the whole system more financially capable. Even without the carbon credits, though, the system is viable. Another way of saying what I said before about life cycle analysis is, from Ian Lyon's point of view, before he started this, he was carbon positive. He was buying purchased electricity, he was burning waste oil, and we've never actually done a life cycle analysis on his whole operation, but it's something like what I'm about to say. He's now drawing down. So each year now he is carbon neutral, and he's also drawing down a couple of years worth of his previous history. Yeah, so each year he's carbon neutral, and he's paying back
Hmm.
the atmosphere a couple of years at a time each year.
So
Does that make
if
sense?
you run it, I guess 9 months of the year, and you run it for most of the day. I assume in the winter you have to move things more quickly and so on. Annual biochar production and consequent carbon offset look like?
Do it again, Pete. It's breaking up quite badly, actually, at the moment.
um,
Badly
so
indeed.
if you're, I don't know if you have these numbers offhand, but what does it look like a annual production of bio and annual carbon offset kind of uh, kind of thing?
So some, it's still early days, and we'll see what the maximum capacity of this first system is that we've put at Hollow Fresh. But the numbers are something like this: a couple of thousand tonne a year, dry tonne a year of biochar,
Hmm.
and something like, from a puro perspective, the way they do life cycle analysis, carbon negative, something like 6,000 tonnes a year of CO2.
Hmm. That's amazing. Um, so this is you called the processor the Echo 2. There are actually a lot of applications for this. What are one the most kind of the applications or this situations you're looking to focus on over the course of the next, say, 2 to 5 years? And how quickly are you trying to grow? Where are you trying to grow?
Yeah, initially we'll focus on Australia because that's where we are, and so we want to make sure we service very well these early units where we're still learning. This is new
Hmm.
technology, and we're still advancing the technology every day. So we've had about 100 inquiries since we established the Hollow Fresh demonstration. We've done mini feasibility studies and big and full feasibility studies on about 50 of those. So we've got a reasonable understanding of the sort of opportunities that exist in Australia. We've had a bit of a look at parts of Europe, parts of Western Europe, and a bit of a look at parts of the west coast of the USA. So we're
Hmm.
getting some understanding about where are the biomass residues, where are the soils or the applications that will benefit from biochar the most. Um, and so it's a cloudy picture, so we're still learning. Um, the commercial applications for biochar are still opening up. For instance, 3 or 4 years ago, I probably would not have imagined that putting biochar in asphalt, was going to be a big consumer. But I now think it'll be one of the big consumers of biochar, and it's a very useful way of locking up carbon because the,
Right.
the asphalt is recycled, and so that's a great way again to displace a fossil um, bitumen, a
Right.
fossil fuel, and replace it with biologically based um, biochar. So those applications are still opening up. So the next few applications look like being heat applications because we've proved that. So
Hmm.
so the very next one's going to be heating a local swimming pool quite near where Hollow Fresh is, a
Hmm.
town that's about 50 miles away from Hollow Fresh.
Hmm.
We've been working with them for some time. They've got a European style district heating loop where they
Oh, cool.
heat some of the council buildings, as well as the pool. The pool's it's a cold part of Australia, so they heat their outside pool most of the year, so it's quite a constant load. And they're surrounded by plantation forestry, so there's lots of forestry residue. There's also lots of
Hmm.
potential uses for the biochar as animal feed and for agriculture. Another one we're just looking at the moment is a potato chip factory in Western Australia that currently trucks liquid petroleum gas, a lot of liquid petroleum gas, quite a long distance to make potato chips. They also use a lot of electricity. They're surrounded by forests, plantation forestry, where a lot
Hmm.
of material is burnt every year. Guess what? that's another
Right.
great application for our technology.
Carbon negative potato chips. I'm so for this.
Yeah,
I'm ready to
yeah.
feel. I'm ready to feel really good about eating potato chips. Um, so Peter, we should probably wrap here because I want people to visit your site and watch your video and read about all the wonderful stuff you've done. But I definitely look forward to having you back on the show as you grow. And thanks so much for spending time with me today.
Thanks, Peter.
All right.